In this video we're going to look at a randomized block design and see how that fits into the linear model framework that we are covering in this series of videos. So the experiment that we're going to look at is on zooplankton, and my treatment variable, I'm going to turn it into a factor so that I can set the order of the levels, and then I'm going to show you a table that contains the data. So what we have here is the researchers were interested in measuring how fish abundance affects the abundance and diversity of prey species. And so we've got 3 fish abundance treatments, low, high, and control, and these have been set up at each of 5 random locations in a lake. And the outcome variable in this case, the response variable, is zooplankton diversity. So let's take a look at what the data looks like in a graph. So on the vertical axis we've got our response variable, zooplankton diversity, and then we've got the 3 treatment levels, control, low, and high, fish abundance. These are the treatment levels, and I've connected the points with lines according to the random location in the lake that each set of treatments was studied. So, for example, one location gave rise to zooplankton diversity here when the treatment level was set at the control level, and then the diversity went down to here when the fish abundance was set at the low treatment level, and then it went to here when the treatment level was high. And then at another location, this was the zooplankton diversity at the control level, and this was what it was at the low level, and this was what it was at the high level, and so on. So you can trace out each of the 5 locations here by just following the lines. So next thing we want to do is to fit a model here. And it turns out that in the book they analyze this data set as if it's a fixed effects study, which it isn't. So I'm going to show you a different way of analyzing the data that would be more typical in this type of example, because here location is not a fixed effect, it is a random effect, and so we really ought to fit a model that incorporates that random effect in the model and doesn't treat it as a fixed effect. So we need to fit what's known as a linear mixed effects model, and so that's what this code is here. So we're using LME here instead of LM, and the library or the package that we need to use to find that function is NLME. So you need to make sure this is loaded before you can use the LME function. Where is it? There it is. And then, as usual, you can look up the function if you need any help on the syntax. Okay, so the first argument is the fixed part of the model, and so the fixed part of the model has the response variable on the left-hand side of the tilde, and then the fixed effect predictor on the right side of the tilde. So treatment is a fixed effect in this example. And then the random part of the model, we're just setting up a random intercept for each location, and the locations are labeled as blocks in in this data set. It's this variable here, block. So the block represents the location. So that's how to set up the syntax for fitting this linear mixed effects model. And then we can draw a graph to visualize the model fit. So this is the filled in circles represent the data points. The reason this one looks darker than all the others is because there's 2 points overplotted on each other there. So there's 2 circles there. And then these lines represent the fitted response variable for each of the locations. And you might ask yourself, well, why are there only 4 of them? We've got 5 locations. Well, 2 of them are essentially the same. I think there's 2 here. You can see this line is slightly thicker than the other 3, so there's 2 locations represented in that top line. Okay, so let's test the treatment effect. So is there a difference in the treatment means? So to do that, we're going to use the ANOVA function, just like we did in the last couple of videos. And the output looks a little bit different because I'm actually using, so here, before we were using ANOVA.lm because we were using this lm function to fit the model, but here I'm actually using lme to fit the model. So this is the ANOVA function that I'm using here. So it's a slightly different function and has slightly different output. But we're going to be able to use the numbers from here to do a hypothesis test of a treatment effect. So what we want to do here is, because we're doing a hypothesis test, we're going to lay out our 4 steps as usual. So step 1, null hypothesis and alternative hypothesis. Null hypothesis is that the treatment means are all the same, and alternative hypothesis is that the treatment means are not all the same. Test statistic is given in the ANOVA table. There's 2 F values here, so you might say, oh, well, which one do I use? Well, we're testing treatment differences, so look for the treatment F statistic there. And then third step is the p-value, so there's the p-value. And then fourth step, decision and conclusion. The decision is to reject the null hypothesis in favor of the alternative because the p-value is less than the significance level 0.05. So we conclude that the treatment means are different. And that makes total sense when we look at the data, look at the scatter plot over here, because for the control level, the zooplankton diversity tends to be higher than when the treatment level is set at low, and low is also a little bit higher than when the treatment level is set at high. So unsurprising that we found a significant treatment effect here. We've got another variable here. We've got location, but we don't test for a location effect. That doesn't make any sense because that's a random effect here, and so you don't tend to test random effects. You tend to test treatment effects. Okay, so we've got our model now. We've done an F-test for the treatment effect. We've determined that there is a treatment effect. So now what we want to do is to use the model to make predictions. So what we can do is use the summary function to give us the information we need to be able to make predictions. And what we want to do is we want to make predictions based only on the fixed effects. The locations were randomly selected, then it doesn't make sense to think about predicting for a certain location because that location was randomly selected. It's not really of any interest in this study. What's of interest is how do the the mean zooplankton diversities change as the treatment level changes. So we want to look at the fixed effects part of the model output and do a similar thing to what we did in the last video. We want to look at these estimates and combine them to get predictions for the different treatment levels. The treatment level that's missing, we've got low and we've got high. Control is missing, so control is the reference level. So to get the prediction for the control level, we just look at the intercept. Okay, to get the prediction for the low treatment level, we add the intercept and the estimate for treatment low. So if we do that, we get 2. And then finally, if we want the prediction for the high treatment level, we combine the intercept and treatment high. If we do that, we get 1.38. And it's always worthwhile checking to see if that kind of makes sense from the scatter plot of the data that we drew. So that we're saying the prediction for the control level is 3, so kind of here. So think of averaging over the locations. So the average is about 3. For the low level, it's 2. So again, averaging over the locations, we're getting 2, somewhere around here. And then finally, for the high treatment level, averaging over the locations, we're getting 1.38, so maybe here somewhere. Again, we can get those numbers directly without having to do the hand calculations using the predict function. So if we do that, we just get those numbers here that we calculated by hand before. So that's how to analyze a randomized block design. And the way that we did it was to use a linear mixed effects model.